Somewhere in the universe, a star is dying. Not slowly, not quietly. In seconds, it can release more energy than our sun will in its entire life. And yet, we still don't know when it will explode. A star can live for millions of years, and then suddenly, boom, for centuries. Astronomers tried to catch one at the start, almost always too late. All we saw were the ashes, the glowing debris drifting through space, until April 2024. A supernova was caught as it happened. Not hours later, not days. Right at the moment it began. What they saw might change everything we know about dying stars. To see why this matters, we traveled 24 million light years away to a quiet spiral galaxy NGC 3621. On April 10th, 2024, a tiny point of light started brightening. Fast, extremely fast. Stars don't do that. But this one did. And it was caught by Atlas, not one telescope, 4. Hawaii, Chile, South Africa, scanning the night sky every 48 hours. At 3:21 a.m. an alert went out. In just 5.8 hours, something had changed dramatically. A star had died. Phones buzzed. Computers lit up. Scientists woke in the night. This wasn't just any supernova. It was discovered almost immediately after it began. For the first time, scientists could see the true shape of a supernova before space itself distorted it. But there was a problem. When a supernova begins, its original shape lasts only a few hours. After that, the blast hits gas and dust, distorting everything, forever. Yang and his team knew this might be their only chance. They needed the very large telescope in Chile, high in the Atacama Desert, where the sky is crystal clear. An emergency request went to the European Southern Observatory. Supernova just started. We need to observe it now. Every minute counts. Approved immediately. Hours later, the telescope turned to NGC 3621. Eyes worldwide were glued to screens. Could they catch it in time? Minutes passed. Then the first data arrived. Light from a star, 24 million years away, landing on Earth for the first time. They were witnessing Supernova 2024 GGI. Massive stars survive by fusing elements. Hydrogen, helium, carbon, oxygen, neon, magnesium, silicon, until the core makes iron. Iron is a dead end. Fusing it consumes energy. The star's engine dies. Outward pressure vanishes. Gravity takes over. The core collapses faster and faster, up to 70,000 kilometers, almost a quarter the speed of light. In seconds, the core implodes. Matter compresses. Protons and electrons crush together, forming neutrons. A newborn neutron star is born. And then, something extraordinary happens. The core rebounds. The collapsing core hits the newborn neutron star, and suddenly, everything changes. Material slams into the dense core and bounces outward. A powerful shockwave races through the star. For a brief moment, it looks like the explosion has begun, but then it stalls. Extreme heat tears iron into lighter elements. Energy is absorbed. The shockwave slows, then nearly stops, 100-200 kilometers from the core. At this moment, the star's fate hangs in the balance. Scenario 1. The shock never recovers. Matter keeps falling in. The neutron star grows heavier, unstable. Gravity wins. A black hole forms. No explosion, no flash, just silence. A failed supernova. Scenario 2. The shock comes back to life. It surges outward. The star explodes. A true supernova. But how? Scientists still don't know exactly. One idea: neutrinos, tiny, nearly massless particles. Trillions are released as the core collapses. Most escape. Some deposit energy, heating material below. Convection builds, like boiling water. Enough energy. And the shock surges forward. The star explodes. Another idea: cosmic jets. The collapsing core spins rapidly. Magnetic fields twist and coil. Jets of energy blast from the poles. Like cosmic blowtorches, these jets can drive the explosion, but along a single axis, stretching the blast like an American football or an olive. And this shape is exactly what scientists were looking for in the light of Supernova 2024 GGI. And then, the light revealed something incredible. Not just brightness, but a pattern, a fingerprint of the explosion itself. Yang's team studied it carefully. Every pixel, every wavelength. They were chasing a ghost, the shape of a star tearing itself apart. The shock had survived, but only just. Hours from now, it would be lost forever. The telescope's instruments measured polarization, light waves vibrating in all directions, now aligned, a cosmic signature of the explosion's geometry. And what they saw was not chaotic. It wasn't random. It had symmetry, a clear axis, a direction, a shape. Like an American football or an olive, a prolate ellipsoid. The explosion wasn't messy. It was organized. This was huge, because most models predicted chaos. The neutrino-driven theory, a storm of asymmetric energy. But this was ordered. It pointed to another possibility. Jets of energy, perhaps, twisting and channeling the blast along a single axis. The core had rotated. Magnetic fields had wound tighter and tighter. Energy concentrated, focused, exploding along one axis. And yet, something was missing. Simulations showed jets could wobble. They could twist. They could fail. In 3D, a tiny misalignment could ruin everything. The jet would collapse. The star wouldn't explode. It would just collapse inward. But SN 2024 GGI exploded anyway. Perfectly. Organized. Symmetric. And it challenged what scientists thought they knew. It suggested maybe chaos and order coexist. The jets jitter, but the explosion survives. Energy deposits near the core. Hot bubbles expand, pushing stellar material outward. And that could be the secret. A violent, chaotic engine producing a perfectly symmetric blast. For decades, supernovae were mysteries. Now, for the first time, we had a blueprint. The universe had written it down in light traveling 24 million years, and humanity was reading it. And then, the first light of the explosion hit the telescope. A star 24 million years away, screaming across space. The data came in waves. Every second counted, every frame a clue. The team held their breath. The universe was revealing its secret. The light told a story, not just of death, but of creation, of forces so violent, they shaped galaxies.
Yes,
Yang and his team analyzed every pixel,
core temperature is
every
rising.
color,
Compensate.
every fluctuation.
Reroute power.
The explosion
Stabilize.
had a pattern,
Confirm. Holding.
a shape, not random, not chaotic, organized, symmetrical. It was an American football shape, or maybe an olive, a prolate ellipsoid. Finally, a clue to the mystery. For decades, supernovae had hidden their secrets. We saw remnants, ashes, shadows of what once was, but now the birth cry of a star was visible. It confirmed something extraordinary. The explosion wasn't purely chaotic. Something was guiding it, something inside the star itself. The team compared models. Neutrino-driven explosions, partially asymmetric. Jets from the core could form elongated shapes, and here it was. In the light from SN 2024 GGI, it was clear. The star didn't just explode, it was sculpted by forces deep inside. They watched as the light polarized. Force 2 revealed hidden details, the axis of symmetry, the fingerprints of the blast. Every measurement, every angle, confirmed it. The explosion had direction, a master plan, written in physics. For hours, the data streamed in. Each spectrum, a puzzle piece, and the picture became undeniable. This was a star telling its story, a story that took millions of years to prepare and ended in seconds. The universe had spoken, and for the first time, we could understand not just the what, but the how, the why. This was history, astronomy's holy grail, catching a supernova, as it truly was. And yet, questions remained. What revived the stalled shockwave? Was it neutrinos? Or the chaotic jets? Or something we hadn't imagined yet? The shape gave clues, but didn't answer everything. Science was still chasing the why. Every detail mattered. Every photon counted. The universe had given us a gift. SN 2024 GGI wasn't just a supernova. It was a key. a window into the death of massive stars. And humanity had seen it for the very first time. And finally, the light spreads across the galaxy. The star's outer layers are blown away, glowing bright. For a moment, it seems as if the universe itself is watching. The energy released is unimaginable. Millions of suns couldn't match it. Astronomers study every photon, every particle. Every detail tells a story of life, death, and cosmic forces. Supernova 2024 GGI shows us the universe is alive, that stars have personalities and destinies, that explosions can be chaotic, yet perfectly symmetrical. We see the fingerprints of physics in action. Neutrinos, jets, and magnetic fields dancing together. The universe revealing its secrets, one moment at a time. This is not just science, it's art. The death of a star, more beautiful than anything on Earth. And yet, questions remain. Why do some supernovae fail? Why do others explode in symmetry? How do jets and neutrinos really work together? Every observation gives a clue, but not the full answer. With new telescopes coming online, we may soon witness many more, catching stars in their final moments. And finally, understanding the forces that shape our cosmos. Supernova 2024 GGI was the beginning, not the end. Because in every star's death, there is a story to tell. A story of energy, motion, and time. A story that reminds us we are all part of this universe. And as we watch the sky, we are witnessing history.